Yeah, yeah.
Yes, please.
I can't speak for the country, but I just wanted to bring it.
Okay. Thank you. No. I will be in my office from noon to, well, if people email me, I will be in my office from noon to 3 tomorrow.
And I only have like half an hour of this person.
You just need to email me if I did not key in one of them.
Yeah.
Wait, how do you? Yeah. I still don't know what I'm talking about.
Which is not.
You're just standing there. No, not stupid. You're not stupid. No.
Unknown caller.
Y'all are gonna drive me crazy today, aren't you? It's been outside of this room since this morning.
Oh, well, it was sunny and that's.
So, yeah, just throw it there.
I didn't sun.
Oh, okay. Okay, I'm in the lab. Please turn in your lab. Find homework for this weekend is to get that graded so that I can get it turned back to you. And also have all your grades inputted into Blackboard before the exam. So. Okay. Let me pass around the sign-in sheet. And we will get started because we have lots to get done today. My goal is to finish up all new information today. So, just as a note, the plan for today is we're going to start with specific heat. I'm going to do one more problem that is specifically a heat transfer. That way you have a couple of examples to work from. The second thing we're going to do is then we're going to get into this concept of enthalpy. We actually already got into the concept of enthalpy in the laboratory, but we're going, and so in the laboratory, we calculated the enthalpy of the reaction as the Q of the reaction divided by the moles. That is the method you would use. You would use the calorimeter. You would use this and calculate the enthalpy as Q of the reaction over the moles. if you're doing it experimentally. But we don't want to just throw ourselves in the lab and do an experiment without knowing the possible precautions we need to take. I don't want to walk into a laboratory and have something blow up. So there are methods that we can use in order to calculate the enthalpy of the reaction to get an idea of what the reaction is going to do before we ever set foot in the laboratory. And that is going to be using Hess's law and enthalpies of formation. As we go through these last two today, we're going to talk about exactly what enthalpy means, and we're going to talk about the data, the meaning you can draw from your answers. So let's get started into specific heat. So what is the final temperature when 42.3 grams of water at 0 degrees Celsius and 255.8 grams of water at 76.78 degrees Celsius are mixed? This one I like because it's a little bit different, because one of the things that I mentioned is we're going to just take a moment and we're going to look at this problem. And we're going to see, okay, what am I actually working with here? And when I look at this problem, I would look at this problem and I see, okay, I've got water that is colder, and I've got water that is warmer. So even though they are both water, we still have two substances in a sense when we're talking about calorimetry. Now, going through this, we were told that the mass of the cold water was equal to 42.3 grams, and the mass of the warm water was equal to 255.8 grams. We were told that the initial temperature of the cold water was 0 degrees Celsius, and the initial temperature of the warm water was 76.78 degrees Celsius. We have been asked to figure out the final temperature. Now, again, heat is transferred from the colder object to the warmer object until both objects are at the same temperature. So the final temperature for the cold object and the final temperature for the warm object are going to be identical. And it is because of that fact that we can do the math that we need to perform. Now, I see, when I look at this, I see mass, I see an initial temperature, I see final temperature. Seeing those pieces of information is going to give me an idea that what I need to use is I'm going to use Q of the, in this case, cold water is equal to negative Q of the hot water. Now, Q, we know, is equal to MCAT. So MCAT of the cold water is going to equal negative MCAT of the hot water. Now, in order to be able to complete this calculation, I have the mass, I have delta T, but I'm going to need C. And so I go and look up specific heat for water, and that's 4.184 joules per gram degree Celsius. And since both of our substances are water, that's going to be 4.184 joules per gram degree Celsius. Now I'm ready to plug the data in. So I start with the cold, mass at 42.3 grams. times the specific heat of the cold, which is 4.184 joules per gram degrees Celsius, times T final, which we need to solve for, minus T initial, which is 0 degrees Celsius. That's equal to the negative of the hot water. So 255.8 grams times 4.184 joules per gram degrees Celsius. Times T final minus T initial, which is 76.78 degrees Celsius. Come on, thank you. Setting up the problem will give you partial credit on the test. So even if your algebra skills are rusty, you can get at least a little bit of credit, maybe not a ton, but a little bit of credit by setting up the problem. Okay, I multiply 42.3 by 4.184, and I get 176.98, and that is going to be joules per degree Celsius times T final minus T initial, which was 0 degrees Celsius. That's equal to, I multiply a negative 255.8 times 4.184, and I get a negative 1070.27 joules per gram degrees Celsius times T final minus 76.78 degrees Celsius. Now we do the distributive property. So I'm going to multiply the 176.98 joules per degree Celsius times T final. And I'm going to multiply 176.98 times 0. Which gives me 0 joules. I then multiply negative 178 or negative 170, negative 1070.27 times T final. And I multiply that negative 1070.27 times a negative 76.78. I rearrange this equation so like units are on the same side, meaning the joules per degree Celsius will be on one side and the joules by itself will be on the other side. So 176.98 plus 1070.27 is 1,247.25 joules per degree Celsius times T final. That is equal to 82,175.33 joules. You then solve for T final by dividing both sides by the 1247. And you get a value of 65.9 degrees Celsius. So the cold water winds up going from 0 to 69 or 65.9 degrees Celsius, and the warm water drops from 76.78 to 65.9. I'm letting everybody catch up with the writing, and then I'm going to go over the math one more time. Okay. So the first thing I did is I realized that I had two substances because I had hot water and I had cold water. I listed out the information because listing out the information gives you insight into what type of mathematical problem you're going to have to do. And what I noticed is I basically had MCAT for cold water and MCAT for hot water. Meaning I'm dealing with a heat transfer problem. And anytime you're dealing with a heat transfer problem, the heat of the reaction is equal to negative heat of the surroundings. It doesn't matter who you pick as reaction and who you pick as surroundings, technically. As long as the Q's are opposite in sign. I then plugged in what Q meant, which is MCAT, into the equation. And then I plugged in the data into MCAT. And don't forget, delta always means final minus initial. So that's why it was T final minus T initial. I then multiplied the mass times the specific heat to get 176.98 joules per degree Celsius. And over here, I multiplied the negative times the mass times the specific heat to get negative 1070.27 joules per degree Celsius. I then did the distributive property, which means you're going to multiply this number by each of the values inside the parentheses. So I multiplied the 176.98 times T final, and then I multiplied the 176.98 times a negative 0, and that gave me negative 0. I did the same thing on the other side. I multiplied negative 1070.27 times T final, and I multiplied the negative 1070.27 times a negative 76.78. I then rearranged this equation. So like values were on the same side. In other words, I moved this negative 1070.27 times T final over to the left-hand side. And therefore, since this was negative, when it moves to the left-hand side, it becomes positive. So that's why it's a positive 1247.25. I moved the negative 0 joules over to the product to the right-hand side. Well, you move a negative 0, it becomes a positive 0, which in this case didn't matter. And then I divided both sides through by this negative one. Divided both sides through by this 1247.25, which gives me just T final and gives me 65.9 degrees Celsius. Questions? Do as much as you can because there is partial credit on this problem, on a test, on this style of problem. So if your algebra is rusty, do what you can and you can still get some partial credit. One of the biggest mistakes I see is number one, people don't understand the distributive property. But the other biggest mistake I see is people forget about that negative. You can't forget about that negative because that is half of the story. The heat from the left side has to be the same as the heat from the right side, but they are opposite in signs. Yes. No, it wouldn't have mattered who was, it doesn't matter who's on the left and who's on the right, as long as you keep their data together. Yes.
So if we go over solving, we know we're going to invest as far as so during the math, we have to have like these units in the equation.
I don't count off during the math if you don't have the units. If that answers your question. Okay. So now we're going to talk about enthalpy. Enthalpy is represented with a capital H. It is known as the heat of reaction. The reason it is known as the heat of the reaction is because it is directly related to the heat of the reaction. If you go back to what we did in the lab, it is related to the heat of the reaction. It's related to Q. So it is frequently referred to as the heat of reaction. Enthalpy is a state function. Basically, state functions depend upon the identity of the reactants, the identity of the products, and the amount of reactant and product. It is that last piece. It is related to the amount. And I'm going to flip back to it, but I'll be right back. That we took in the moles when we calculated the enthalpy in the laboratory. So it's related to the identity of the reactants, the identity of the products, and the amount. And it's called the heat of the reaction. What this means, what a state function is. I could talk about a state function of a drive from New York City to Los Angeles, California. All that would matter is that I started at New York City and I ended at Los Angeles, California. It doesn't matter whether I took New York City down to I-40 and went all over down. It doesn't matter how I got there. All that matters is where I started and where I ended. That's what a state function is. Energy is another example of a state function. It doesn't matter where you started and where you ended. It depends on how you go. So that's why it depends upon the identity of the reactants and the identity of the products. Now again, it also depends upon the amount of the reaction. Let's think about this from an explosion. I can have a single firecracker. It's going to give off a certain amount of energy, right? But if instead I light an entire row of firecrackers, is it going to be more or less energy? Or the same? It's going to be more. That's because I had more firecrackers to start with. So that's why the state function then depends upon the amount of reactant and product. Now, enthalpy can be described as endothermic or exothermic. And I'm going to put this in a table. So with respect to enthalpy, a favorable reaction will be an exothermic reaction. Whereas an unfavorable process is an endothermic reaction. An enthalpy that is favorable will be a negative delta H. Whereas a positive enthalpy will be unfavorable. Now, favorable compared to unfavorable. Why? Why is a negative a good thing? A negative is a good thing because it means more energy is produced than is needed for the reaction to proceed. Whereas if we're talking about unfavorable, energy must constantly be added to the reaction to make the reaction proceed. Let me go back to my fireworks example. Fireworks, my firecracker is an exothermic process. Yeah, I gotta give it a light, but once it gets that light, it goes. Even if we take a long row of firecrackers, once you give them a light, they tend to go. That's an exothermic process. An endothermic process would mean that I would have to constantly be standing there with the lighter until it explodes. Because it needs me to continuously add energy. It will not occur on its own. So firecrackers are exothermic because they will go off on their own as soon as you give them the light. Whereas if it were endothermic, I'd have to constantly be adding energy to it. It wouldn't want to occur on its own. Therefore, an exothermic process means that heat is a product. Where an endothermic process means that heat is a reactant. Okay. Again, enthalpy can be figured out. I hate that it changes things on me. Enthalpy can be figured out by experimentation like we did in the laboratory, but it also can be determined using Hess's law and enthalpies of formation. So now I want to discuss Hess's law. Basically, what Hess's law does is it uses a series of reactions to calculate the enthalpy of an unknown reaction. Or I should say the unknown enthalpy of a new reaction. Some of the keys is if you flip a reaction, you change the sign of the enthalpy. If you multiply a reaction by a coefficient, then you multiply the enthalpy by the same coefficient. So let's see Hess's law in action. Calculate the enthalpy for 4NH3 gas plus 5O2 gas goes to make 4NO gas plus 6H2O gas, given N2 gas plus O2 gas goes to form 2NO gas with a delta H equal to a negative 180.5, and that's kilojoules per mole. Second one is N2 gas plus 3H2 gas goes to form 2NH3 gas with a delta H equal to negative 91.8 kilojoules per mole. And 2H2 gas plus O2 gas goes to form 2H2O gas with a delta H of a negative 483.6 kilojoules per mole. This is a Hess's law problem because we're actually going to calculate the enthalpy of a reaction given a series of reactions. Now, the way to do this. Let everybody get caught up writing. And I am going to be using highlighters and colors. It'll help. Okay. The first thing I'm going to do is I'm going to find I have NH3 gas. So I find the equation that has NH3 gas in it. And it just so happens to be the second equation. Here, the gas is a reactant. But here, the gas is a product. So one of the things I'm going to have to do is I'm going to have to flip this equation, which I'm marking with an F. The second thing I note is that I have 4 NH3s that I need, whereas this equation only has 2 NH3s. So I'm also going to have to multiply this by 2. So I'm flipping this equation and I'm multiplying by 2. So I get 4 NH3 gas is going to go to make 2 N2 gas plus 6 H2 gas. And I do the same thing. Now, because I flipped it, this becomes positive. Because I multiplied it by 2, That means that it's now 183.6. Going back to my original equation. The next thing I see is I have O2. Well, unfortunately, I have two sources of O2, so I'm going to leave that alone for now. So then I go to the fact that I have NO, and I'm going to find an equation with NO in it. Now I have only one equation with NO. NO is a product here, and NO is a product here. So I don't have to flip the equation. But I note that I have 4 NOs and I only have 2 in my equation. So that means I am going to have to multiply this equation by 2. So I'm multiplying the equation by 2. So 2N2 gas plus 2O2 gas goes to form 4NO gas. And because I multiplied the equation by 2, I multiply the delta H by 2. And that's a negative 361. The last thing I note is that I have water gas. So I find an equation with water gas. My water gas is a product, and it is a product here. So that's good. It's already established in the right direction. But what I see is I need 6 of them, and I only have 2. Therefore, I have to multiply this equation by 3. So that becomes 6H2 gas plus 3O2 gas goes to form 6H2O gas. Since I multiplied the equation by 3, I multiply the delta H by 3. So folks, all I've done so far, I'm trying to make sure, is my target reaction, I use this target reaction. With that target reaction, I needed NH3, so I found NH3. Here, NH3 is a reactant, but here it was a product, so I had to flip this equation. Here I needed 4 of them and I only had 2 of them. So I also had to multiply that equation by 2. So that's where this equation comes from, and that's how I got a delta H of a positive 183.6. The O2, I needed O2. Well, I can't do anything with the O2 yet because I had more than one source of O2. If you have more than one source of an element or a substance, ignore it in your target equation. Move on. So I moved on to the NO. I found a reaction that had NO. I wanted it as a product. Great, it's already as a product. So I didn't have to do anything as far as the direction of the reaction. But I I needed 4 of them and I only had 2, so that's why I multiplied the entire equation by 2 and the enthalpy by 2. I did a similar thing with the water. Now, if you did it correctly, you can check yourself. Because another term, one way you can think of a arrow, a yield, is as an equal. So you have, if we take and add it up, on the left-hand side, we have 4 NH3 gas plus 2 N2 gas plus 5 O2 gas plus 6 H2 gas. That's on the left-hand side of that equals. On the right-hand side, we have 2 N2 gas plus 6 H2 gas plus 4 NO gas plus 6 H2O gas. Now that I have added it all up, left-hand side stayed on the left-hand side, the right-hand side stayed on the right-hand side. Now, I'm going to cancel out anything that appears on both sides. Just like we did with the complete to net ionic, we got rid of the spectators. We're going to get rid of the things that appear on both sides. So the N2 gas is going to go away. The H2 gas is going to go away. And if I did this correctly, then once I got rid of the things that appear on both sides, you will notice that I got out the target equation. Now, the enthalpy for this target equation is going to be the sum of the enthalpies for the 3 equations added together. We added the 3 equations, we're adding the enthalpies together. And this enthalpy comes out to be a negative 1,628.2. Again, we added the equations together to get the target equation. So we add their enthalpies together to get the enthalpy of the reaction. Because of time, I have just made a decision. Hess's law will not be on the exam. But you will see something similar to Hess's law next semester in college chemistry too. But I will not put Hess's law on this exam. Now, the enthalpies of formation will be on this exam, but I think you'll find them a lot easier to do. Okay. The enthalpy of formation is officially the enthalpy of 1 mole of material produced from its elements in their standard state. What do we mean by standard state? Well, solids and liquids are just straight out whatever they are. But a gas, it means that it is under 1 atmosphere. And a solution means that it is 1 molar in concentration. So for example, I would combine 2 hydrogen gases, because that is the standard state for hydrogen, plus 1 carbon solid to make CH4 gas. Notice it is 1 mole of substance. Or, whoa, where did that go? Or I could take hydrogen gas plus 1/2 of an oxygen gas to make water liquid. Notice I'm making 1 mole of the substance from its elements in their standard state. Now, elements in their standard state have a delta H of formation equal to 0. So when I made that 2H2 gas plus carbon solid going to make methane gas, if I look up the delta H for this, for methane, the delta H of methane is negative 74.8 kilojoules per mole. That negative 74.8 is all due to the methane, because hydrogen in its standard state is 0. Carbon in its standard state is 0. So literally this negative 74.8 is completely due to that methane. That's why it's called an element, or it's called a enthalpy of formation. How 1 mole is formed from its elements in its standard state, therefore the enthalpy is strictly associated with that element or that compound. You can look up these enthalpies of formations in a table. We can get pretty much a ton of different things formed. Now, enthalpies of formation can be used to calculate? Really, it's an estimate, but to calculate the enthalpy of reaction. To do so, the enthalpy of the reaction is going to equal the sum over the products of the enthalpy of formation times their moles minus the sum over the reactants of the enthalpy of formation times their moles. You are given this equation on the exam. You don't have to memorize it. You have to know how to use it. So let's look at an example. Calculate delta H of reaction for 2CO gas plus O2 gas goes to form 2CO2 gas, given your delta H is a formation in kilojoules per mole of CO, which is a CO gas. Pay attention to the state of matter. The state of matter is important. Almost said the state of matter matters. The state of matter is important. CO gas is they didn't give it. Negative 110.5 O2 gas, because it is an element in its standard state, is 0. And CO2 gas is negative 393.5. Using our delta H of reaction, that means that it is going to be the products. Well, that is, the product is CO2. There are 2 moles of CO2 times negative 393.5 minus, there are 2 moles of CO times negative 110.5 plus 1 mole of O2 times 0. So it's a negative 787 minus negative 221 Therefore, the answer is negative 566 kilojoules. You will be giving your delta H as a formation in a table. You just have to plug it into the equation. Let's look at another example. Calculate the enthalpy of reaction for CH4 gas plus 2O2 gas goes to form CO2 gas plus 2H2O liquid. Again, pay attention to your states of matter. Given delta H is a formation at in kilojoules per mole of CH4 gas, which is, I said it earlier, negative 74.8. O2 gas is 0. CO2 gas is negative 393.5 kilojoules per mole, and H2O liquid is negative 285.8 kilojoules per mole. So our delta H of reaction is going to equal the products. I have, and it's always the products, 1 mole of CO2 times its value of 393.5 plus 2 moles of H2O times negative 285.8 minus the reactants, which is 1 mole of CH4 times negative 74.8 plus 2 moles of O2 times 0. So the delta H of reaction equals negative 965.1 minus a negative 74.8. So therefore, this reaction, the delta H for this reaction is equal to a negative 890.3 kilojoules. Folks, this negative means that it is exothermic. Heat is a product. And it is favorable. The reaction is favorable to occur. Let's look at example 3. And I want you to calculate this one. I'll give you the data and I want you to do it. Calculate the enthalpy of reaction for 2H2S gas plus 3O2 gas goes to form 2H2O liquid plus 2SO2 gas, given the enthalpy of formation for in kilojoules per mole of H2S gas is negative 20.1. O2 gas is 0. H2O liquid is negative 285.8. And SO2 gas is negative 296.1. While you're calculating, I'm going to say, don't forget your calculator Tuesday. Nobody will have time to share theirs. So you will be out of luck. Okay, if you did your math correctly, you should have gotten a negative 1123.6. Again, I do ask this question on the test. Oh, well, series of questions. Negative means that it is exothermic. It means that heat is a product. It means that it is favorable. If that had been a positive value, the opposite would have been true. So you have to not only get the answer, but you've got to interpret the answer. That's where that table came into play that I put up there earlier. You've got to not only answer the question mathematically, but you've got to interpret the answer. So again, no Hess's law will be on the test. But enthalpies of formation and calorimetry will be on the test. You will use, by the way, you will use enthalpy of formation again in college chemistry too. A lot of what we have learned, you will use again in college chemistry too. Yes. Am I having office hours today? Well, my schedule just loosened up a little bit, so I will be in my office until 1:30 today. I will also be in my office because I have been asked to be in my office. I will be in my office from 12 to 3 tomorrow. You too.